This section is about polynomial functions and their graphs. So what we're going to be doing here is we are going to be trying to sketch graphs of polynomials. And when you graph a polynomial, before you do anything else, you need to find four things. Our first thing that we need is what's called the degree. And the degree of a polynomial is going to be the exponent of its highest term. And by highest term, I mean the thing that has the highest exponent. The next thing I need is my leading coefficient. And my leading coefficient is going to be the coefficient of the highest term. Then the other things I need are going to be my zeros, which, if you remember, are also called x-intercepts. And when I have zeros, I'm going to need to find if they have any multiplicity that's not 1, which I'll talk about in just a few minutes. So some zeros will have something special about them. And the last thing I need is my y-intercept. So let's do an example now. We have f of x equals 3x to the third minus 6x squared minus 9x. We're going to be finding the degree, the leading coefficient, the zeros, and the y-intercept. So the degree is always going to be the highest exponent, which in this case is going to be 3. Now, even if you had this out of order, it would still be whatever the highest exponent was. Like if the 9x came before the 3x cubed, the degree would still be 3. The leading coefficient is going to be the coefficient of my highest term, and my highest term in this case is the thing with the 3 exponent. So my leading coefficient is the 3. The next thing is my zeros and my y-intercept. So the y-intercept's a little easier, so let's do that one first. And you probably remember this, hopefully, that you find the y-intercept by setting x equal to 0. So what we're going to do is we're going to take our equation. By the way, I'm going to change my f of x to y. And we are going to set x equal to 0. And once you do that, you're going to find that actually your y is going to be 0. So your y-intercept is going to be at 0, 0. So the last thing we need to do is our zeros. And remember, the zeros are called x-intercepts also. And you find your zeros by setting y equal to 0. So what I'm going to do now is I'm going to factor this. I can start by factoring out a GCF of 3x. That is going to give me x squared minus 2x minus 3. And when I factor that, I end up getting 0 equals 3x times x minus 3 times x plus 1. If I set each factor equal to 0, I get that my x values are 0, 3, and negative 1. So I am going to have x-intercepts. These are my zeros, by the way. Since they're x-intercepts, I'm actually going to write them in x-intercept form. So I have one at 0, 0. I have one at 3, 0. And I have one at negative 1, 0. So I'm going to now talk about the leading coefficient test. And I'm going to tell you right now, this looks a lot harder than it actually is. There's going to be a few little rules that you have to remember. They do look really complicated, but they're not that bad once you get the hang of them. So with the leading coefficient test, tells you is it tells you how the ends of the graph behave which we call end behavior, depending on the leading coefficient, that's what LC is, and the degree. So this is going to tell you what's called our end behavior. So if I ask you for the end behavior of something, you're going to have to think about what the leading coefficient is and what the degree is. So our first situation is when you have a positive leading coefficient and an even degree. So I'm just going to give you an example so you can think about what that would look like. So for example, if we have y equals x squared, that our leading coefficient is 1, it's positive. Our degree is 2, it's even. So from there, if you remember, the graph is going to look like this. It's going to be a parabola. And actually, anything with a positive leading coefficient and an even degree is going to have the same end behavior as y equals x squared. So sometimes you're going to see it listed as like up and up because each end goes up. So it looks like that. That's going to be our end behavior there. The like super professional way that you'll see it written is something along the lines of as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity. The big thing that you're going to need this for is going to be to help you graph. So let's go on to the next example, a positive leading coefficient and an odd degree. So for example, if you have y equals x to the third power. Now hopefully you remember that that graph is going to look like this. I didn't draw it that well, but hopefully you remember what it looks like. So this one, oftentimes you'll see it listed like that. And if you want to write it in the really, really like nice way, we would say as the really mathematical way, as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches negative infinity. So if you're not 100% clear about what that means, what I mean by x approaching infinity is I mean x going to the right. So as x is going to the right, remember x is right, left and right, y is up and down, y is going to go all the way up. And for the second one, as x approaches negative infinity, that's to the left, y approaches negative infinity, which means down for y. So it's kind of a similar idea to when we learned domain and range, that y is up and down, x is left and right. Okay, so we have two more. The next one is if we have a negative leading coefficient and an even degree. My example here is y equals negative x squared. This one, the degree is 2, which is even. The leading coefficient is -1, which is obviously negative. So that one looks like this. And everything that falls into this box is going to have an end behavior that's similar to that. So you might see it written like that with two downward arrows. And if you were to write this out, we would say as x approaches infinity, y approaches negative infinity. And as x approaches negative infinity, y also approaches negative infinity. So our last one is if we have a negative leading coefficient and an odd degree. For example, if you have y equals negative x. Now this one, don't forget the degree is 1 because it's kind of like there's an invisible first power here. The leading coefficient is -1. So that one, when you draw it, if you remember, it looks like this. And everything else is going to follow, everything else with a negative leading coefficient and an odd degree is going to follow that format. You can write it like that if you want. So the super mathematical way to write it would be as x approaches infinity, y approaches negative infinity, and as x approaches negative infinity, y approaches infinity. So now we're actually going to be sketching a graph. So one thing you might notice is that this is the same thing that you had from example number 1. And so you actually already had a few things that will be helpful here. So in the previous example, we found that the degree was 3, the leading coefficient was 3, we found 3 zeros and a y-intercept. So now I'm going to be using the leading coefficient test to help me figure out what the end behavior looks like. And what we're going to notice is that my leading coefficient, which is 3, is positive. My degree, which is also 3, is odd. So what that means is that my end behavior is going to be of this form, which means that as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y also approaches negative infinity. So, so that's going to be helpful for drawing this. So I'm going to start by drawing my zeros. So I have a point at 0, 0. I have a point at -1, 0. And I have a point at 3, 0. Actually, my y-intercept is already done. It's at 0, 0. That one is both an x and a y-intercept. The other thing I know is that my end behavior is going to be down to the left and up to the right. So what I'm going to do is I'm going to go down to the left, and I'm going to go up to the right. And that's going to be from my furthest left 0 and my furthest right 0. Then from there, all I need to do is the only thing I have now is that I'm going to pass through my intercepts, and I'm not going to pass through the x-axis in any other place. So actually, it's going to go up and over, and then it's going to go down there. Now, this is not drawn to scale. You'll notice I didn't actually draw a scale on the y-axis. What you'll find is that actually this might even go down a lot further than it is. But for now, I want you to worry about getting the shape correct. So I want you to get the shape, and I want you to get the zeros. Don't worry so much about what the points in between are. Now we're going to talk about multiplicities. And by multiplicities, I mean repeated zeros, which I'll explain in just a second. So we actually have two types here. And our first rule has to do with when the multiplicity of a 0 is even. In that case, we're going to have a bounce in our graph. And I'll show you what I mean by that. So let's do an example. So for this example, I have f of x is equal to x to the 4th minus 6x to the 3rd plus 9x squared. So remember to find zeros. We are going to be setting our y or our f of x equal to 0. And then from there, we need to factor. And when you factor, you're going to start by factoring out an x squared, which leaves you with x squared minus 6x plus 9. From there, I keep my x squared out there. And then x squared minus 6x plus 9 is going to be x minus 3 times x minus 3, which actually gives me x squared times x minus 3 squared. So you might notice that we're going to have a few things doubling. So like, for example, I have x squared equals 0. If you have something squared equaling a value, that is the sign of a repeated 0. So this means that I have my first 0 is x equals 0, and it has a multiplicity of 2. The other one I have is I have x minus 3 equals 0. If you want, you can work this out twice, although you don't really need to do that. It's kind of like extra work. So when you do that, you get x equals 3 and x equals 3. So rather than writing down x equals 3 twice, we're going to write that our 0 is x equals 3 with a multiplicity of 2. So let's put everything together, and we're going to now graph. And in order to graph, we now need to do, once again, we need to do several things. So you need to find the zeros, which we just found. Those are our zeros. You need to find the leading coefficient. It's going to be 1, and the degree, which is going to be 2. In this case, I have a positive leading coefficient, and I have an even degree. And that means that my graph, both of its tails are going to go up. The other thing, remember, that you needed to find was your y-intercept. In this case, the y-intercept is actually pretty nice. It's just going to be 0, 0. If you want to know how I found it, you just are going to plug in 0 for x and find the y. So let's go ahead and use this to draw it. So we're going to draw our, it's a combination x-intercept and y-intercept. If you want to write these as points, you can. And that's going to be at 0, 0. We're going to have a point at 3, 0 also. So now let's discuss what will happen now. So we know that our end behavior is going to have both sides going up. That's the first thing. The other thing is that we know that both of these zeros are multiplicity 2. If you look back at what I said before about multiplicity of 2, or of even multiplicity, that means that I'm going to have a bounce. So what's going to happen is right here at 0, 0, it's actually going to bounce back up. And the same thing is going to happen at 3. So this is actually going to be almost a W-shaped. So now, if your multiplicity of your 0 is odd, we're going to have, I just call it a squiggle. There's no real technical math term for it. And I am going to give like a little condition here. If it's odd and more than 1, I'll show you what to do if it's 1 actually in just a sec, or you might be able to figure it out. It's going to have a squiggle. So let's do an example. For my example, I have f of x equals x to the 4th minus 2x to the 3rd. To find the zeros, you are going to set f of x equal to 0, and then you are going, this is supposed to be an equal sign, by the way, then you are going to get factor out the x to the 3rd, which gives you x minus 2. My zeros here, you're going to set x to the 3rd equal to 0. However, this is a repeated one, a repeated 0. It actually repeats 3 times. The other one, you're going to set x minus 2 equal to 0, which just gives you a normal 0 of x equals 2. So our zeros are going to be x equals 0 with a multiplicity of 3, and x equals 2. That one actually has a multiplicity of 1. You don't need to write down that it has a multiplicity of 1. It's automatically assumed unless you write otherwise, but you can if you want. Okay, so let's go ahead and draw this graph. So a few things. My leading coefficient, by the way, is 1, which is positive. My degree is 4, which is even. It is actually going to behave the same way the last one behaved. The other thing is if you find your y-intercept, it's at 0, 0 again. So let's go ahead and draw this now. And you'll notice I'm just kind of sketching it quickly. So I have an intercept at 0, 0. That's a y and an x-intercept. And I have another intercept at 1. Or at 2, I'm sorry. So let's go ahead and talk about what's going to happen. So let's do the one at 2 first. The one that's a multiplicity of 1, actually, that's just going to pass straight through. So it's going to go down like that. I know that because of my end behavior. It passes straight through. It looks just like you had on example number 2. Now, I'll stop here and go from the other side. The other one, what's going to happen on the other side is it has a multiplicity of 3, so it's going to have the same end behavior, but now what's going to happen is it's going to kind of be almost a squiggle like that. So it's going to be a little bit different. And so it looks like that. You'll notice that maybe I didn't draw it pronounced enough, but it should kind of almost be like this. So if you want to draw it like a major squiggle like that, that's fine. If you think about the graph of y equals x cubed, it's kind of like the way that one's supposed to look. So we have one more thing in this section. And this is a rule about zeros. We're not going to be graphing for this. We're just going to be writing some equations. So our rule is that if you have something that is a zero of a function, then two things will happen. First of all, if you evaluate f at that 0, your answer is going to be 0. That's what that means. The other thing is that if you do x minus your 0, that's actually going to be a factor of f of x. So if you don't quite understand what I'm saying here, hopefully you'll get it after I do an example. So let's go ahead and do one. So we're going to do 3 problems where we're writing equations of a polynomial with the given zeros. The first one I have is 3, -4, and 0. So these are going to be zeros, or you can also call them x-intercepts of my polynomial. The way that we are going to do this is we are going to write these as f of x is equal to x minus 3 times x plus 4 times x minus 0. And actually, you're just going to go from here and you are going to simplify. That's all you need to do on these problems. So I'm going to rewrite this as the x minus 0. I always like to just put it in front as an x times x minus 3 times x plus 4. In my opinion, it's easier to FOIL these two first. It's always a good idea to look and see what would be the easiest to work with and do those first. So I'm going to get x times x squared plus 4x minus 3x minus 12, which gives me x times x squared plus x minus 12. And then I end up getting x to the third plus x squared minus 12x. So my final answer for that equation is f of x is equal to x to the third plus x squared minus 12x. And that's how you would write your answer. By the way, just to comment, don't go back and factor this. It's just extra work and it'll take you back to where you started. So leave it like that. That's going to be the simplest form that we're looking for. Okay, we're going to do 2 more of these and then we're done. Okay, so this next example, I have 3, 5, and -3. So my function is going to be f of x is equal to x minus 3 times x minus 5 times x plus 3. So actually in this one, if you have 2 things that are the same number and opposite signs, it's easiest if you do those first. Those are going to give you a much nicer answer than if you were to do like the x minus 3 and the x minus 5 first. So if you recognize that you have 2 things that are the same number with the opposite sign, you probably are going to want to do those first. So when I put these together, I get x squared plus 3x minus 9. Looks terrible so far, but it's going to get really nice. So I end up with x squared minus 9 times x minus 5, and then I'm going to just FOIL it one more time. So I end up getting x to the third minus 5x squared minus 9x plus 45, and this is actually my final answer. So then my last problem, I have the square root of 2, 3, and negative square root of 2. As with the previous one, I noticed that the square root of 2 and the negative square root of 2 are probably best to be put together first. So I'm going to write this as x minus square root of 2 times x plus square root of 2 times x minus 3. And when I do that, I am going to get x squared plus root 2x minus root 2x Square root of 2 times square root of 2 is just going to be 2, or you can write it as square root of 4, but then it'll become 2. So actually this problem got really nice because my radical 2's are going to cancel out. So now I just need to simplify it out by foiling. I end up getting x to the third minus 3x squared minus 2x plus 6, and that's my final answer. It's always nice to write it with an f of x or a g of x or something, so I'd recommend that you do that when I ask you for a polynomial function. And this is my final answer.